Hey, there we go. For some reason, my settings got changed back to default, and that apparently was not actually set for this microphone. So I have no idea what's going on. At any rate, good evening. This is Obi-Wan Pez for Simplex Pachinko. How y'all doing? Hey, Nerdist, welcome in. And Matthew, good evening. Had to scroll past all the music notes there. Alright, so, as I said, maybe we'll be allowed to stream. My son is not acting very well tonight, so he may decide that he wants to be as disruptive as possible. So, hope everybody's week has been going alright. Yeah, I wasn't here last night because my computer decided that it wanted to do Windows Update. And I'm like, you know that's not going to work. And it doesn't listen to me. So, weird. So we ended up sitting here until about 10:30, waiting for the computer to finish doing Windows Update. By the time it was done, pretty close to 11, I was just like, this isn't going to work. So ended up hanging out with the boss lady and a few other people and had a lovely evening, but not my intended activities for the night. And then tonight, yeah, my youngest decided to flip out and have a temper tantrum, so. Although I found out, it seems that stoicism is the way with him. Because I let him flip out. I just sat there and basically meditated, blocking his doorway so he couldn't go anywhere, and he got bored and started reading a book. I'm like, huh, okay. Who'da thunk? Let him yell at me, let him scream in my face, whatever. Just, doesn't affect me. So, anybody have any preferences for the evening as far as material to cover? Fair enough, Matthew. Let's see. So tonight is 2022-04-28. Man, that sucks. I'm sorry, Nerdist. What's worse, the neighbor kids are exacerbating the situation with his behavior. So it's like, great, okay, well, you just lost privileges to go see your friends. Seems to be the only way. Oh well. Alright. Well, let's start with what I did today in Calc 2 because it's awesome. And then we'll go from there. And I know I've done this a few other times, but nonetheless. Every time I come back around to it, it's just like, yeah, exciting. So, we were talking about power series. And how our power series is going to be the infinite sum of some set of polynomial terms, each with a coefficient out front, and then a power term. So if we plug in 0, this ends up being a sub 0 times x to the 0, so we'll just leave that blank. And then add in a sub 1 times x to the first plus a sub 2 x squared plus a sub 3 x cubed, and so on and so forth. Now this is an infinite series, so looking at this, if the values of x are at all large, or if the values of a potentially affect the values of x more than just like, oh, it's a constant. If there's a particular like type of constant that it can be, and we'll talk about that in a bit, then it could potentially change the behavior of this entire function. But, you know, generally, this series will converge for the absolute value of x being less than 1. So if we have, oh, and these are real valued, so we're not going to be doing any complex valued equations, or non-real. Right, and all of our a sub n are going to belong to the reals as well. So all of our a sub n and all, well, our x will belong to the real numbers in some way, shape, or form. So generally speaking, absolute value of x being less than 1 is going to cause each of these individual terms to start getting smaller and smaller as we go further and further out. Now it is possible that there are larger values for x which will end up converging based on some sort of function transformation or lots of other stuff. Yep. Well, if they do. So when we're just talking about, like, numbers that are absolute value less than 1, then yeah, that's exactly what it is. And of course this also works if it's not a fraction, if it's just some sort of decimal, but again, same reasoning. If you take, you know, 90% of 90% of 90%, you're talking exponential, and it's just going to decrease. Right, and then again, the other way is that there's some value for, or some scheme for our a values, which cause it to then drop at the same rate or faster than an exponential function, like x, x to the n, which then could potentially converge the entire series. So we looked at a couple of power series in class, and we said you got something like, you know, n equals 0 to infinity of 1 over 2 to the n. Right, this is going to be equal to 1 over 2 to the 0 is just 1, plus n is 1 makes this 1/2, plus n is 2 makes it 1/4, 1/8, 1/16, etc. And it turns out that this value, if you take the infinite sum, is equal exactly to 2. Alright, and if you look at it like sort of intuitively, it makes sense because you go a distance of 1, then you go halfway to 2, and then you go half of that distance that's left over, and half that distance that's left over, and half of that distance that's left over, forever and ever and ever. So eventually we get as close as we could possibly get to 2 without actually being there, infinitesimally close to 2, and then we just say that, yeah, the limit is going to make this go to 2. So we also looked at other sorts of functions, like if n goes from 0 to infinity of, let's see, Bertram! Oh no! What's going on? Parentheses. No. Damn, you are correct. Alright. Alright, so if we go... I mean, there is a non-negative remainder if you have a finite number of terms. But if you have an infinite number of terms, it equals 2. That's not really what you're talking about, is it? Okay. Let's see. Over, we did n plus 1 raised, or times 3 to the n. Alright, so this is a power series. It looks a little awkward just because it's in this weird... It's not in the standard format, it's in a slightly weirder format, but it's cool. So, here we've got n equals 0 going to infinity. We've got 1 over n plus 1 times 3 to the n, and then that is being multiplied by x minus 2 to the n. So this is shifted, but it's the same kind of deal. It's in the same format as the power series up top. So we can say that, yeah, this is a power series, and we want to figure out what is the radius of convergence for this. So for what values of x will this series converge? Alright, so in Calc 2 we did a whole bunch of tests just before this, and we talked about what the different methods are for figuring out whether a series at all will converge or diverge. Basically, if it has a finite number of terms, it will converge, right? Finite number of finite terms, then they're going to converge. If you have an infinite number of terms, you can converge, like this one up here, or 1 over 2 to the n. And for this one, we want to say, well, in this case, there can be some values for x for which this will converge. So one of our tests was a ratio test, which says that provided that our function is going to have values that decrease as we go on. So in this case, we can tell that n being larger is going to cause more stuff in the denominator to get larger faster. And then our x to the n, again, if we assume that we are within the radius of convergence, so let x be close to 2 for the first part, then yeah, these are going to also be small and then get smaller. So then we want to just figure out how large is it going to be. But, and our limit eventually has to go to 0. So looking at this, our limit is eventually going to go to 0, because again, if we're within the radius of convergence, then this power term is going to go to 0, and 1 over all this stuff with n is eventually going to cause the fraction to go to 0 too. So with both of these parts going to 0, we can say, yeah, okay, this is going to work, provided that we find the right x values. So our ratio test says that we're going to have this value that we term rho, which is equal to the limit as n goes to infinity of all that stuff. So we say that the ratio test, I gotta be careful with that, sorry. Take the limit of the absolute value of the ratio is on top is going to be a sub n plus 1, and on bottom we compare the ratio to a sub n. So we're looking at successive terms. What's happening? And this has 3 outcomes, naturally. So rho could be between 0 and 1. In which case the series will converge no matter what, because we're saying as the limit, we're taking the limit as n goes off to infinity. So if n goes off to infinity, then the ratio of those two values should get closer and closer and closer to maybe closer to 1 or closer to 0, but either way it's going to drop into some value where our values are getting closer to 0. So if it's sufficiently fast enough, it will go to 0 fast enough, and this will cause it to converge. If rho is equal to 1, this test is inconclusive. And we gotta try another. And rho could be greater than 1, or rho could be equal to infinity, which technically it's the same thing, but they put it as a separate deal. Whatever. And in this case, the series diverges. So then we got to look at this and say, all right, for that particular series up there, what's going to happen? So we could take this as parentheses x minus 2 to the n plus 1 over m plus 1 times 3 to the m plus 1 divided by, I want to take the limit as n goes to infinity of the absolute value of all this stuff, and that's going to be equal to rho. It's terrible here. So if you were, so here's the thing, with this one you're not going to, and it's pretty obvious. When we plug all these things in, things are going to start getting knocked out of place. Anyway, the main point is that basically the ratio test and the next one, which is called the root test, is going to be looking for patterns which have multiplicative differences, or, well, they're going to have ratios, constant ratios, or higher ratios that go from one term to the next to the next. So in the case of an exponential function, like we see here, where we've got 3 to the n in the denominator, because we have 3 to the n in the denominator, that's going to tell us, oh look, this has a multiplicative pattern to it. Masahide, how's it going? So since it has a multiplicative pattern, the ratio test is perfect for it. The problem is if you were to have, for instance, something like a rational function. If you have a rational function, then what you're going to get is the ratio of your successive, or not successive, the ratios of your leading coefficients is going to tell you what's going on. But if all you're doing is saying, I want n plus 1 plugged into the function, and it's a rational function, then you've got a polynomial up top and a polynomial on the bottom. Right? It's literally going to be the same thing. It's just that one of them is like n to the fourth, and the other one on top is going to be n plus 1 to the fourth. So you get the same function, both top and bottom. It's just that one is shifted. So the ratio between them is 1. So no matter what you do, right? If you wanted to do like, oh, I'm going to be clever and say that my b sub n is going to be, right, like some sort of fraction here of 4n to the third over 6n to the fifth, right, plus 1. Now, we know that this is eventually going to, not only go to 0, but the sum is going to converge. So the difference in successive terms is going to 0 quickly enough that it's eventually going to reach a specific value, a limit value. But if we did this in, like I said, in the ratio test, then here what we get is that this is going to be 4 times m plus 1 to the third over 6 times m plus 1 to the fifth plus 1 over 4 n to the third over 6 n to the fifth plus 1. So if we did this, and then we want the limit as n goes to infinity, here we've got the 4s and the 6s, right? So all of that's going to divide out. If we want to, we can just real quick make this limit n goes to infinity. So real quick here, this is going to change a couple of things. 4 times m plus 1 to the third over 4n to the third, right? And then we multiply by, put that up there, this is going to be multiplied by 6n to the fifth plus 1 divided by 6 parentheses m plus 1 to the fifth plus 1. Which again, when you take the limit as n goes to infinity, you're going to end up with n plus 1 to the third over n to the third. You're taking the limit as that goes to infinity, that's 1. And then down here, we look at it in terms of 6n to the fifth plus 1 over 6 parentheses n plus 1 to the fifth plus 1. And again, take the limit as that goes to infinity, it's 1. So rational functions, and more specifically polynomial functions, don't have a multiplicative pattern which can be exploited by the ratio or root tests. They have additive patterns. So if you remember adding, when you do like a table for a polynomial, every time that you increase by 1 on your x side, then your y side is going to increase by a specific value. Now, in the case of quadratic functions, it ends up being that you're just adding a different odd number, usually. You know, basic quadratic. You're going to be adding a different odd number every time. There we go. And then the differences of those differences is going to be constant. So you're always, adding 2, for example, to your change in y's to get from one to the next. So Mesahide, we're talking about power series. So this is the lead up to the most important thing you could possibly learn in Calc 2. What you up to? Alright, and then on the bottom we do x minus 2 raised to the n, all divided by parentheses m plus 1 times 3 to the n. And again, we can rearrange just as we did up top. Limit as n goes to infinity. Alright, just as we did up top, this is going to be the x terms, so x minus 2 to the n plus 1 divided by parentheses x minus 2. That's not an x. X minus 2 to the n. Alright, multiplied by n plus 1 times 3 to the n divided by n plus 1 times 3 to the n plus 1. I'll exchange that for something more reasonable in the next step. So limit as n goes to infinity of, here, this is just going to be x minus 2. Then over here, we're going to get n plus 1 over n plus 2. And then over here, we get a 1/3. So 3 to the n divided by 3 to the n plus 1, we got one spare 3 left over at the bottom. Yes, we can definitely do something more basic and interesting. Hope I have something interesting for you. And Bertram, you said you wanted something. Alright, so when we take this, the limit as n approaches infinity is actually going to pass right through the x minus 2 part because it doesn't affect it. There's no n that's a part of x minus 2, and so it just passes right through. This 1/3 is going to be on the bottom of it. So we got absolute value x minus 2 all over 3 times the limit, seriously, as n approaches infinity of n plus 1 over n plus 2. Now this is a nice easy one. The limit as n goes to infinity of a number that is 1 less than the one below it. So 1/2, 2/3, 3/4, 4/5, 5/6, etc. starts approaching a value of 1. Right? 999 over 1,000. 9,999,999 over 10 million. It's all approaching 1 as n gets much, much bigger. So all this is just going to be 1. We can effectively ignore it. So our rho value is going to be this thing. Alright, so what we want is that we want to find when this converges. So a series will converge if its rho value is between 0 and 1. So 0 is less than the absolute value of x minus 2 all over 3 is less than, and we could have it equal to 0 on this side, is less than 1, strictly less than 1. Now, for absolute value functions, normally we focus on that anyway. Alright, so here's something that you could do in pre-calc. Right, you've got the absolute value of something less than 1, so how do you solve it? Well, first of all, the constant here, if we remove it, we can, the absolute value of a times b is going to be equal to the absolute value of a times the absolute value of b. So here with the fraction of 1/3, we could have actually just kicked it out way back here. It's all good. So 1/3 times the absolute value of x minus 2 is less than 1. And yes, is greater than or equal to 0, but at the same time, it needs to be anyway, but based on the absolute value. So whether or not you write it, it's not a big deal. All right, and then here, we need to solve for x. So here, multiply by 3. Also, hence why I said you don't really need it. Okay, so if we multiply by 3 in all these places, then we end up with just the absolute value of x minus 2 is less than 3. And again, I'm just going to make it smaller and smaller until it disappears. Okay, now one of the things that I'm famous for here, is saying, okay, there's a nice alternate method to solving absolute value inequalities, and that is that we can say that we want to find the definition of absolute value is the distance between two objects that we are subtracting. The difference between them is the distance between them. So x and 2. So x is an unknown value. We don't know where it is. 2 is going to be our sort of like target value. That's where if our x value is 2, we get a distance of 0. So that's going to be like our center point. This is where stuff is happening. All right, and then our distance must be less than 3. So we need to go 3 in this direction. And 3 in this direction. And if our distance needs to be less than that, we need to be closer to 2 than either of those two endpoints. So open at -1, open at 5, and shade in between. So this is the OB method. So again, distance between x and 2 is less than 3. So these are our acceptable values. All numbers that are between -1 and +5. Now there's something else that's weird with power series, and that is that it is possible that either of the endpoints could still work. So, yes. So the other thing that I tell my students, right, this is method A here. Method B is that you follow the definition of absolute value. Do not do that little thing that your high school teachers have been teaching you for however many years, since I was in school, probably well before that, probably since my parents were in school. Okay, absolute value of x minus 2 is less than 3 means that I don't even want to bring it up. It's the whole flip change sign thing. It's stupid. I hate it. Don't do it. So the left side, the definition of absolute value. We've done this before on stream, I know that much. So x minus, you know what, let's do c. Okay, so the definition of absolute value of x minus c, yeah, that thing. Don't do that. All right, is equal to. If you get a positive number out of this, that means that x was bigger than c. And that means that x minus c is just going to be what you get. Okay, so this is what we got. The definition of absolute value, it's just x minus c if x is greater than c. It is negative parentheses x minus c, or if you want to, you could also write it as c minus x. So you exchange the order in which you subtract. If x is less than c. Yeah, the keep change flip thing. Don't. I think that's what it's called. Don't do it. I don't even know the name because I don't care. It's ridiculous and I hate it. Okay, because students use it all the time arbitrarily and have no idea what they're doing. So, the definition of absolute value. That thing over there. Shh. All right, subtract things in a way that makes them positive. Done. Right? So, subtract things in a way that makes them positive. So this is what we got here, which means that we've got two options. Either x minus 2 is less than 3, or negative parentheses x minus 2 is less than 3. And again, you can automatically do it if you feel like it, but I prefer doing it from here so that you get into the habit of always making it this stuff. Notice, that doesn't change at all. It's both of them is less than 3. Both of them are less than 3. So we're going to keep getting that no matter what we do. Which means over here, I'm going to make that a negative x plus 2 is less than 3. And now, I'm going to make my x positive. So over here, I'm going to add 2 to both sides because my x is already positive. And x is now going to be less than 5. Aww. That's fine. Over here, I'm going to add x to both sides. And I'm going to subtract 3. This means that over here I've got a negative 1 is less than x. And then what's going on between them? Again, what you really need, you have to have a conjunction here. You have to have some sort of logical connection between the two sides. Now, when I was writing this, I said or, which is wrong, but this is what you're saying. You're saying, I need these two statements. Now, if you get all the way to the end, you can look at this and say, okay, what are these statements? This is negative 1, this is positive 5. So x is less than 5, which means it's like this. X is greater than negative 1, which means it's like this. If this is an or statement, it's covering the entire numbered line, and so it doesn't make any sense. Therefore, it needs to be an and statement, which only covers some, the place where they overlap each other. So it's going to only be this stuff in here. This has to be and. Alright, the other way to think about it, you're out here and you're saying, I want the distance to be less than a certain amount. It has to be within this range. Alright, give me a minute. No. Just looking for a stuffed animal around the room. There was a request to find a stuffed animal. That's a good question. Where did he leave it? Well, I can't find it because it's not here. Man, I can barely find X. Right, there we go. Okay. So anyway, we've got these, right, intervals that are going to tell us where we can have the radius of convergence. So for what x values is that original power series going to converge? So we got this thing here, the x minus 2 raised to the n all over n plus 1 times 3 to the n. So we said that the radius of convergence of this thing is 3. So we said that everything has to be within the distance of 3 from our center value, which was 2. Yep. Yep, so distance from 0 of that whole expression, x minus 2, or the distance between x and 2. I usually prefer saying that, at least in this context, just because it's a little bit easier to work with in terms of, like, you know, where is my center point and where am I going from there. So our radius of convergence is 3, but the interval of convergence, again, here we said that we have x values that are between -1 and 5, but we didn't check those two values. So we're guaranteed that all the numbers in between -1 and 5 are going to work just fine. But now we look at this and say, okay, what about at -1? What about at 5? Well, this ends up becoming a little bit more obvious when we actually do it out. Right, so 5 minus 2 raised to the n all over parentheses m plus 1 times 3 to the n, and goes from 0 to infinity. So here we can look at this and say, well, this is going to be the same as sum from 0 to infinity of 3 to the n over n plus 1 times 3 to the n. Well, those are going to go away. And now you're just left with the sum from 0 to infinity of 1 over n plus 1. Now the interesting thing about this is that this will diverge. So despite the fact that, and this is something that we did in class a couple weeks ago. So despite the fact that this will go to 0, right? 1 over n plus 1, take the limit as n goes to infinity, it's going to be 0. The problem is that if you were to actually write out all the values that you get for this, so n is 0 gets you a 1, plus 1/2, plus 1/3, plus 1/4, plus 1/5, plus 1/6, plus 1/7, plus 1/8, plus, and then keep going on and on and on. There's an interesting thing that goes on here. These two values here, 1/3 and 1/4, are going to make a sum which is greater than a half. Right? This one here is a half, and this one here is just 1. Right? These 4 numbers here are going to make a number that is greater than 1/2. Right? 1/8 plus 1/8 plus 1/8 plus 1/8 would be 1/2. A 5th plus a 6th plus a 7th plus an 8th is going to be greater than 1/2. Likewise, the next 8 terms are going to be greater than 1/2, and the 16 terms after that are going to be greater than 1/2, and 32 terms after that are going to be greater than 1/2 when you sum them all up. We can keep doing this forever. Like literally, this is an infinite series. It's going to keep doubling its distance in order to get a half. But there are now an infinite number of halves that are going to be added together forever and ever and ever. So this will diverge, meaning that the limit as n goes to infinity of all of our sums, so we can call those, usually we call it partial sum, is going to go off to infinity. Yep, I mean this is a, rational function, and that one is an exponential, so it it's the way in which it's, yeah. It's the speed at which it goes to 0. So that's also the same thing with the Koch snowflakes. So you end up with, if you were to draw a triangle like this, oh, it's a great triangle. Hey, there we go. Thank you, computer. So you start with a triangle, and you say that every iteration, what we're going to do is we're going to take all the... Really? Sure, now you won't do it. Every iteration, what we're going to do is say that the middle 1/3 of each line on the triangle is going to be erased, which I don't have. Really? It's going to be erased and then replaced with a line of equal size that's coming up and then going down. So making a new equilateral triangle that's coming out of that space. Why? It's awful. Alright, seriously, let's turn that off for a sec. Don't enhance. Okay. So anyway, goes like this. Oh yeah, it's beautiful. All right, the middle 1/3 of each of these then gets erased and replaced with an equilateral triangle. Stop enhancing it. It's replaced with an equilateral triangle. Okay, then the next one over, it does the same thing. So then each of these is gonna get another spike on here on each of its flat surfaces. And then on the next iteration, each of those again, if you're doing this actually with like, well, you can do it on a computer much more easily, but So the Coke snowflake, which looks like this, and again, this goes infinitely. So every time we add a new interval, all of those straight lines get another, you know, cut out the middle third, and then cut out the middle third, and then make an equilateral triangle off of it. So as we go, you could actually draw a circle. I don't know that it's going to be circumscribing like the original six-pointed star. I think it still goes outside of that, but you could, there will exist some sort of circle that you could draw that this shape will never exceed. So here, this has a finite area. But if you were to add up the distance that you're traveling along each of these parts, and again, doing this forever and ever and ever, you're going to notice that as we get further out, the distance that we're going around the snowflake does not, like, cease. It's going to keep getting bigger and bigger and bigger. It's just going to keep getting infinitely large. So we're going to have an infinite perimeter. So it typically ends up being something like this. Yeah, like, I can. I don't say I necessarily want to. Yeah, the problem with this is that now we're getting like, yeah. So the problem is that as an infinite series, the perimeters, yeah. You can look it up online. The perimeters here end up being, again, it's like you make the original one a distance of 1 around all the edges. Just makes it easier. And then the distance that we go up like this is going to be here, root 3 over 2. No, that's even smaller. Right, it's not even that. So yeah, this distance here, that's a third. So that's going to be root 3 over 6. It's going to be that distance there. So root 3 over 6. And then that distance over here is going to be, see, that was a third, right? So that's going to be a third of a third is 1/9. And that's going to be root 3 over 9 then. No, it's twice that. Root 3 over 18. Which makes sense, right? Because every time you go down one layer, all of our distances are going to get cut in thirds. There we go. I mean, you're not, though, really. Because although you're subtracting this 1/3 that's here, you're just adding 2/3. So you're just adding a third of the size of whatever you cut out. Or you add the size of whatever you cut out onto the outside. Yeah. You know, it's a net gain of plus that. And then times the number of sides that there are. So that's the key, really, is that our distances are all getting cut in thirds, but there's going to be triple as many of them every single time. No, it's not even triple. It's more than that. 6 times. So we went from 3 to 6 spikes, and then to 12 spikes. Okay, so we're just doubling. Well, anyway. So over here, the interval of convergence is showing us that 5 is going to diverge. And then when we try the same thing on -1, -1 minus 2 to the n over n plus 1 times 3 to the n. This is now going to be sum n goes from 0 to infinity of -3 parentheses to the n over n plus 1 times 3 to the n. Now these don't cancel out. No, not immediately, because -3 is an alternating series. So half of its terms are going to be negative, half of its terms are going to be positive, and they keep flipping back and forth and back and forth. In this case, what we can have now is that we can say, and goes from 0 to infinity, this is the same as -1 to the n times 3 to the n, divided by n plus 1 times 3 to the n. Oh look, 3 to the n's go away again. So now, this ends up being n equals 0 to infinity of -1 to the n divided by n plus 1. Now somebody might say, well, that's just the harmonic series again, it should diverge. It seems like it, but the -1 raised to a power is going to change something here. So this thing is going to end up being 1. Nope, not plus. Come on. So minus a half, plus a third, minus a fourth, plus a fifth, minus dot dot dot. So we're just going to keep alternating whether we have positive or negative, and then our numbers are getting smaller as we keep going. So 1 over 2, 1 over 3, 1 over 4, etc. just keep getting smaller. The limit of this thing is that it's going to go to 0. So our 1 over n plus 1 has a limit of 0. And because of that, what's going to happen is we start from 0, and we go a positive distance of 1. And then from here, we go back a distance of a half. Then we go forward, a distance of 1/3. And then we go back a distance of 1/4. Then we go forward a distance of 1/5. Backward a distance of 1/6. Forward a distance of 1/7. Backward a distance of 1/8. Right, so this is going to keep working its way back and forth, and every time we do this, we're going to keep getting closer and closer and closer to a specific value. You know, I haven't actually punched this into Wolfram. Nope. Sum of alternating harmonic series. Natural language. Go. It is the log of 2. Natural log 2. I think I heard you from here. What? Yeah, so anyway. Yeah, maybe you've heard this one before. Anyway. So yeah, we get the natural log of 2. Which again is a finite number and all that good stuff. So this one does get us a convergent value, and so we can include -1 as part of the interval of convergence. but then we have to exclude 5. Anyway. So yeah, interval of convergence here is going to be from -1 to +5. Any x value that you want to include, any x value you want to use, which is inclusive -1 to exclusive +5, is going to allow that particular power series here to converge. There was one other thing that I wanted to show, but whatever, it's fine. This already took long enough. Alright, does anybody else have something else they want to talk about before... before we try something else that's interesting and easier? Alright, I am also going to try a bite of these pickles. They are pickled in the same jar as habanero peppers. That was not too bad. Yeah, I mean, it sure beats all the junk food I usually eat. Went to the store tonight and just bought, like, a whole bunch of slightly healthier food. Yep. Yeah. My diet, there was a time, shortly after having my gallbladder out, where, like, you know, 90% of my diet was, like, vegetables and water, or coffee or tea, which are close enough to water. I mean, yes, it's a diuretic, so it takes out the water from your body, but still. Ooh, there's one. Yep. I think a corner of that one was rubbing up against a pepper or something. Or I caught a seed. Ooh. It's a bit of a spike. Alright. I'll wake you up. Mood, right? Really, I think I just need to go to bed, like, as soon as stream is over. But of course, that's boring. Alright. So what I'm going to do is talk about a couple of things that I saw about the unit circle. in the last pass that we did. So this last go through. Don't do it, it's a trap. Alright, now we can actually use that enhance shapes here. So, in the unit circle, it's just ridiculous. Alright. Sort of. If you believe it, then totally I did it. Or you're just swearing at the fact that I drew the circle. Do you mean that it's perfect? Because that's totally not me. Yep, so on Microsoft Whiteboard they have this new feature that was enhance inked shapes. So I turned that on. Alright, so if we go to the origin and we put out our terminal side of the angle. So our theta is going to go from here to here. And again, our x and y values are going to be here. So we have this distance here. It's going to be x. This distance here is r. No. Wow. No. It is y. I don't know how that happened. And then this distance here is r. Which we're going to let it be 1 because it's the unit circle. It makes things a little bit nicer. Okay. So based on this, we also have a few important things that we can make. So one of the things that I did originally was I took... Hang on, let me copy this. Let's copy. Okay. Now that I've copied. So what I did originally was I said, alright, let's take this. Let's draw a tangent to the circle. That's going to be vertical. And this distance here is literally the distance of the tangent of theta. Alright, so going from the side of the circle straight up gets us a tangent to the side of the circle, and then that connects with the point where the terminal side of the angle goes out. Works pretty nicely. Okay, then the distance that's covered between the origin and where the tangent meets is what's called the secant. So that's our secant line. And again, provided that we're on the unit circle, these are equal to the function, the trig function values. It also means that down here we've got x, which is going to be equal to the cosine of theta, only on the unit circle. And y being equal to the sine of theta. Alright, that also means that we could draw a tangent horizontally close enough. Alright, so this is going to be the cosecant of theta. Here we still have r is 1. And then the distance from the origin all the way out to where the cosecant meets, that's backwards. That's backwards. Sorry. Oh, man. Sorry. Cotangent of theta. And the cosecant is theta here. Right, so you could do it several different ways. So one of them is that here you're just saying like, oh, I want the cotangent, which is going to be like a horizontal tangent. And you could say all sorts of whatever. It doesn't really matter. That was all kind of BS. I was trying to make up basically an excuse for making this work. Yep. So alternate interior angles, because here this is parallel to that. We also have theta here. Yep. And again, all tangents are right to their axes, because the axes are radii of the circle. Right, and then here you've got all three Pythagorean identities in one disgusting picture. I mean, it's not awful, but it's just a little cluttered. Right, that's going to be one there. So, I already knew most of this from, previous semesters doing my promotion project, which I still haven't heard anything about. Whatever. Alright, so if we go like this... Yeah, I'm going to need to pull that down. Anyway. So, a different way of doing this, which I saw in the book and I was like, that's horrible. But now that I've actually, looked at it, it looks way better. Yes, you can also find, there's one that I like that shows all of the, it highlights this y distance here and just calls it sine of theta. It highlights this x distance here and just calls it cosine of theta. And then likewise for all the rest of the trig functions, it highlights all the pieces in this format. Now that I've actually seen this and thought about it harder, I like this other one better that I'm about to do here. There we go. Here. I have to be perpendicular to the camera. So we still do the sine and cosine the same way. So our x and our y are related to, again, equal to cosine of theta here is equal to the sine of theta here. However, where they draw the tangent is the place that it makes sense to draw the tangent. Wherever your angle is. So you start from here, and then you draw the tangent out like this. This is now the tangent of theta. And this is now the cotangent of theta. And then here, the right angle that we have, or the length that we have here is the hypotenuse of this right triangle made by the tangent, the secant, and 1, r equals 1. And now in this particular case, your radius is common. So unlike this picture over here where we had for the cotangent, our radius was vertical, and for the tangent, our radius was horizontal. It's kind of ugly. So instead, they just said, okay, let our terminal side be our 1. And then from there, you can build the tangent on one side, the cotangent on the other. This is a much more useful and concise picture. It doesn't start messing around with all this other stuff. Which then also means that the line that goes from the origin to where the cotangent, in this case, meets the y-axis, is going to be our cosecant of theta. Right, and that's the other thing, is that the secant and the cosecant aren't overlapping with the radius. They're the distances along the axes, which are, again, in both pictures, they're literally secants to the circle. They go through the circle twice. It's just that they also happen to go through the origin. Right, that's what makes them special rather than some random secant that I just draw here. Right, that's a secant, but it's not the secant. It has nothing to do with the angle in particular. So let's see. Anything else that I need here? No, that's pretty much it. So right, and the Pythagorean identities are all right here. It's almost staggeringly obvious when you see it like this, and then say, oh. Right, and then again, with this picture, you can also say, oh, right, this is now going to be pi over 2 minus theta which is the complementary angle to theta. Which also means if you want the tangent of pi over 2 minus theta, this is going to be equal to the cotangent of theta. Right, the cotangent of theta up here is just the tangent to this angle. Likewise, the cosecant of... Nope. Secant. Likewise, the secant of this particular angle, pi over 2 minus theta, is equal to the cosecant of theta. So use all the cofunction identities to make this work. Alright, and then if you really needed to go all the way back, you could also say, so I started doing this semester, I started talking about the sine, and then I immediately went to the tangent, and then I immediately went to the secant. And then, you know, somebody was like, what about cosine? And I said, oh, you want that thing? Okay. So if we draw in this dotted line here, and we say, what is the sine of pi over 2 minus theta, right? It's just so natural to work in the cofunction identities now. Before it was like, here's the thing we gotta remember, and there was no real understanding or connection, even on my part. But with the picture, it really cleans it up, like I said. You know, what's the sine of this weird angle? Well, that weird angle is up here. So the sine of that is equal to our horizontal distance here on the unit circle, which is then equal to the cosine of theta, which is x. And then there was something else that I learned. I think I did it last year, but I forgot. It's been a long time. Right, and the only difference is that now you have to expand it out and say it's, you know, r tangent theta is going to be this blown up version. Monkey monkeys. So actually I was just showing the original of what I used to do for showing all 6 trigonometric functions in one picture, which is really kind of gross and nasty, and it shows like these really cool Pythagorean triples, but I'd have to really separate this out to make it make sense half the time, just because there's so much clutter. But by altering where we put the tangent, so instead of having the tangent be a tangent to the circle, a tangent to the circle at the end of the axis, instead I was like, wait, I understand this picture now that I've been staring at that somebody else did for years. If we make the tangent of the circle the tangent to the terminal side at the circle, then that goes down like this, and again, that distance is called the tangent. We can actually let that be the tangent at theta. Then there was another thing that I learned. Again, I kind of discovered it, rediscovered it. It's been known about for a very long time, but still, the cosine formula for alpha plus or minus beta gets you your cosine alpha cosine beta minus plus sine alpha sine beta. So when we do this, what I'd wanted to do was try to figure out what the sine of alpha plus or minus beta was. And I was having a kind of, it was unsuccessful. Let's just go there. It was unsuccessful because I was looking at this and trying to say like, okay, how can I alter my two angles to make them come out to be the thing that I want to? And it was just ridiculous, and it didn't really work. Cosine definition of the dot product. Nice. Okay, so here we can say, well, what if we wanted an angle that was the complement of that angle? So pi over 2 minus parentheses alpha. Let's just do, well, we can do it either way, it's fine. Plus minus beta like that is going to be equal to cosine of, now in this case, rather than try to split this in a particular location, I'm going to reassociate in the front here. This is the, nope. This is the cosine of pi over 2 minus alpha plus or minus beta. Wait, nope, minus plus. And that, man, that's actually important this time. So, let me move this just a little bit here. Stop. Just want to move this stuff. I don't understand why this is so hard. I did it earlier. Wait. Was it the mouse? Is that why? Yeah, okay, it's the mouse. That's why I did it. Alright, so let's get rid of this bit here. And then say we're going to come back to that. Okay, so this was what we wanted, the sine of alpha plus or minus beta. So the sine of alpha plus or minus beta, we don't have an expression for it at the moment. We say, okay, let this be pi over 2 minus that angle, parentheses alpha plus or minus beta, which then allows us to reassociate with here, pi over 2 minus alpha as our first angle, and then beta as our second angle. This is going to be the cosine of pi over 2 minus alpha times the cosine of beta. This is minus plus. Yeah, this is minus plus, so over here we're going to get a plus minus. This is going to be the sine of pi over 2 minus alpha and the sine of beta. Barely. Okay, so then this is going to be equal to cosine of pi over 2 minus alpha is just the sine of alpha times cosine beta plus minus. This is the sine of pi over 2 minus alpha is going to be the cosine of alpha times the sine of beta. So then this means that the sine of alpha plus or minus beta is going to be equal to sine of alpha cosine beta plus or minus cosine alpha sine beta. Yeah, I was trying to do all sorts of stuff to try to prove this at one point, and I said, like, why don't we try making the angles tilt over to the y-axis, because then if everything's relative to the y-axis, then we should be able to, like, manipulate the stuff and make it work. Yeah, no. It just came out with the same cosine formula. So that was a little embarrassing. I was like, okay, well, we didn't waste that time because you all got a good practice in doing algebraic manipulation. So it's very regional dependent, but I will say I was offered 2 jobs. I had just earned my master's. I had started in the county schools, in public schools. Yeah. So I'd started working in our county schools with a bachelor's and no experience, or like, you know, a half a year experience essentially, plus some sub work, and they started me at 40,000. This was also 15 years ago, give or take. So started at 40. I was making 30 something at the corporate company. A little bit after that. Technically, I think I was making 36 or 38, but they prorated because I only worked 30 hours instead of 40. So then, once I got my master's, they offered me, it was high school, and now it's 2-year college. So, as a high school teacher, they started me at 40. As a college teacher, well, I was an adjunct first, so I needed to work on that. That basically, I knew that I wasn't making money to, like, pay the rent. I was teaching so that I could get experience. Like, that was the main thing. I was in a in the same 2-year college doing adjunct work. It started somewhere around between 2,300 and 3,200 per class per semester. So somewhere in there, give or take. And that was, again, I was a bachelor's. I had my bachelor's, and I was at the lowest rank of our adjunct levels. In fact, never actually leveled up. I should have, just never did. So some of our people do actually go to like 4 different institutions and get 1 adjunct class per institution. I can't say that I recommend that. So that's different. I'll let you know in a minute. Once I got my master's, I was able to teach at a 2-year college. Full-time. And so the 2-year colleges allow you to work for them with masters. I started there, and again, I was offered a similar position at the corporation that I was working at. Yeah. So the corporation I was working at was going to hire me to work in the fraud detection department of their insurance credentialing division. So basically making sure that healthcare providers were not double charging people, and if they were, run an audit to make sure it wasn't done on purpose, or if this is like a regular thing. You know, well, it's always this patient, or it's always this person at this particular practice. You know, always double codes or something like that. So basically that was one job, and the other was become a full-time math professor, or well, it was originally instructor at this 2-year institution. So I went with teaching because I knew that that's where I wanted to be. That's where I wanted to put my effort. And I decided to start teaching there. I was offered both jobs at $50,000, and that was 10 years ago. 11, whatever, it's fine. So a little bit more than 10 years ago. But you're right, if you want to work full-time at a 4-year institution, you need to have a PhD. If you don't, you can still be in their particular scheme, right? You could still be a lecturer or something like that if you have your master's, but you're also limited to which classes you can teach. So, for instance, I would be probably limited to teaching anything in the bachelor's level, and most likely, until they got to know me better, some of the basic stuff. So like algebra 1 through whatever algebra classes they have, all the way through calc, maybe up through differential equations because I've taught it a bunch. But yeah, they don't just like trust anybody with any class. They're pretty selective. Mm-hmm. I was wondering, but so we need to be there 7.5 hours every day for 5 days a week. Although lately, with the pandemic and all that, it's been a bit less. So we've had to have, I think it's at least 50% in-person hours. All right, one sec. I'm gonna step away for about a minute here. I'm gonna press the button. So give me like 1 minute. All right, we're back. Yes, thank you for indulging me. That's actually the first time that I actually pressed the button. So, yeah, I do have to correct papers. I'm not particularly great at it, but it's something you got to do. So, yeah. So like I have to do minimal prep for basically any of my classes at this point because I'm teaching the same 4 classes that I did last semester. I have to make exams for my classes at least just for the one that I coordinate, which is pre-calculus. So next semester my partner in crime is leaving our institution, so I am going to have both pre-calc classes on my plate that I'm going to have to make exams for. Did you at least get to like give the rest of those questions to other people so that like you corrected question 1 and that person corrected question 2 and that person corrected question 3? Or is it like really bad? Hmm. Yeah, that's always key. If you can spread out the workload, especially if you have a giant class like that. So I mean that means you're averaging 70 students per section, or were there more or fewer than 4 sections? I guess how many students do you have personally? Hmm. So, I mean, it depends on what your goal is. If your goal is to make money, you don't go into education. You go into consulting. Nice. I kind of wanted to TA when I was in my undergrad, but I was never really like supremely good enough to like do something like that. So I instead went to our audiovisual department, and I took our equipment and hauled it across campus. And I loved that job. That was great. I really liked it. I learned so much about not just like the teachers and the students that I never would have seen. So like we had regular customers who were in like women's studies, other sociological, social sciences, the music department. Oh man, the music department needed so much audiovisual. I mean, obviously, right? But they just needed so much help. Even the lecturers in the music department needed so much help, like getting their computer to connect with the system. It was just insane. I mean, TAs and adjuncts have it way worse, but yeah, that's the other thing is like I personally have very little incentive or like care about how much I'm making. Like I have basically zero incentive to like maximize my pay. I'm doing what I really love. Yes, my working conditions I'm sure could be slightly better, and I'm sure that my pay could be better, but like I'm gonna let the salary and benefits committee work on that. You know, I will support them in whatever way I can, but like I'm not going to be the guy who's going to jump up there and be like, I deserve 20,000 more a year. I'm also not the breadwinner of my family. Like that is not my goal. If I wanted to, I should have gone into the insurance industry and done the fraud detection department. Because if I was working on neural networks to discover, fraud detection algorithms and stuff like that, like I could be at the top of the field doing awesome presentations at conferences all about neural networks and things like that. But that wasn't my goal. You know, it would have been cool. I probably would be making over $100,000. And I am most certainly not. Yeah, I love the neural network class we had. So my spouse and I both took it. I as a math major and she as a computer science major. And it was such a great class. I loved every minute of it. And then when I went into my differential equations classes in the next in the same semester, I was also doing partial, and in the next semester, I was also doing nonlinear differential equations. And I did a which one was which? For one of them, I did a Cahonin self-organizing map, which I showed on stream at one point. It was basically like, your RGB colors represent the predator, prey, and scavengers in a particular biological system. And so I just played around with some of the stuff until it managed to break horribly. And then my nonlinear class, that was the nonlinear class, I think. The partial differential equations class, I did something else that had something slightly to do with it. I don't even remember what it was at this point. It wasn't very good, but, I tried. So anyway, yeah, so at my level of experience, I am getting... So we have 4 grades of like what 4 grades of what your like status could be at our institution. So instructor is when you just get hired and like you don't have really any experience. You have assistant professor, which is basically you have either some experience and you're coming in and just hired, or you have your 3 years of experience as an instructor and you did a project. So basically you do like this. You do like a little portfolio that's like, what did I do during my 3 years here? And so as long as you do that and it's reasonable, you get hired, you get your permanent contract. Now I say permanent, it's not really permanent technically, but What's MLOps? NLP is nonlinear programming, right? I think. Machine learning. Oh, yeah, okay. So yeah, you get assistant, and then you do a 3-year project, and you can go for associate. And then once you get associate professor, you do like a 4-year project, and there's a whole bunch of requirements after that, part of which includes 400 hours of CEUs. So, you know, your continuing education credits, continuing education units. And my old boss was like, look, if you're gonna do 400 credits, like 400 CEUs, it's pretty much that you are going to get either another master's or a doctorate. Like, that's pretty much your 400 hours right there. Continuing education credit. Continuing education unit. There we go. So you have to do something which shows that you're like taking this thing, whatever project you're working on, super seriously. So again, either you're going to get a new master's or a doctorate, approximately. So it doesn't come out to... It doesn't come out to like, oh, you have to do a degree. You could do a whole bunch of classes that just are disconnected, but they have to relate to your field. So like if I went back and took a whole bunch of classes on like machine learning, AI, and stuff like that, I'm not sure it would count because it's not really like my field. But at the same time, it could just be like they just want you to do something really awesome. And, you know, maybe my boss now would be like, yeah, that's totally going to count because, you know, it's just furthering your education. Most of the time, most of our teachers will go and get their education doctorate or a math doctorate. Because, and most of the time it's education, because they're teaching. Oh, man. Yeah. I've been playing While True Learn on my PC. That's pretty intense. And there's always an option whenever you come across a new thing in the game. There's a little box that pops up that's like, here's how to use this in the game, and then here's how the actual math works. Good times. While True Learn. Technically, I think it's formatted like that. At some point, I got it for free on Epic Games, which it's probably not going to come back around at all, or like for a long time, but still, I think it would be worth, you know, I don't even know how much it cost, but I got it for free, like I said, so I was pretty happy to just be like, eh. And I would say it is definitely worth getting it for free, because it is really a lot of fun. Oh, goodness. Alright, we're okay. My frame rate just dropped to red for a second there. Alright. See you, Mega Monkeys. Have a good one. See you around. Store page. LNR problem. Yeah, sure. Mega Monkeys, if you're still here, $13 US. So, whatever that translates to. So I think that's probably about 15 euros, likely. Okay. Okay. Yeah. So if x was 32, for example, what is that in mod 5? So really the big question is, do you know how modulus works? And then in that case, it's just do it. Yeah. Yeah, so it might be worded a little funny, but yep. Yep, so anytime you're doing a division problem, in this case again, 5 into 32, 6, 32, and then remainder 2. So here, your x is going to be your 2, and your 6 is going to be your quotient. Yeah. So they're just saying that, like, it's also possible that you could continue that down, because 32 mod 5 is equivalent to 27 mod 5, which is equivalent to 22 mod 5, which is equivalent to 17 mod 5, 12 mod 5, 7 mod 5, and 2 mod 5. Or negative 3 mod 5, negative 8 mod 5, negative 13 mod 5, negative 18 mod 5, and so on. So it would keep going. And what they're trying to prevent you from doing is saying, oh, well, I can go to negative 18 mod 5, so that's lower than 2. Right, negative 18 is less than 2. So that's why they had to restrict it and say, no, it needs to be the least non-negative in order to say, okay, it has to be either 0, 1, 2, 3, or 4. So I don't think that's what they're asking. I think that they're asking, find the least non-negative remainder for that. So, like, find x. Now, maybe I'm wrong. But as far as I can tell, that's what they're going for. Yeah, 2 mod 5 is definitely 2. But then you're changing what you're dividing. Hey Mogus, how's it going? So, I don't... Yeah, I think what they're asking is just do the problem, essentially. So try to get down to what this is going to be. Right, greatest common... Your greatest common divisor or greatest common factor is going to be 1 because 32 is made up of only 2's and 5 is a prime number. So these are mutually prime. But I don't think you want greatest common divisor at all. Especially since GCD usually only allows integers to be input and integers to come out. Usually. All right. Anybody seen anything else you want to talk about? Oops. Close my own stream. Oh no, let's do some more. If y'all are interested, let's keep going. I got at least another 30 minutes probably in me if we're up for it. That being said, I do kind of want to look up who's on just so I have an idea, because I don't know Thursday nights at all. Yeah, Mogus, let's go for a hard geometry question. It's going to be horrible, I'm sure. Bertram, calc is, I don't know. I always kind of liked the fact that calculus kind of started over in terms of difficulty. Like, you know, going from kind of some of your early stuff, moving up through the higher level math in high school, like getting through Algebra 2 and then Trig. That was all like this massive build-up. And for me, seeing it was kind of like, oh, this is, you know, this is a growing difficulty of trying to do analysis and all this stuff. And then when we hit calculus, we basically started over with all of our difficulty. And it was like, oh, here's a bunch of rules. Now you get to play. So we started, you know, scrambling through and being like, what's the derivative of this? What's the derivative of that? It wasn't even necessarily, I guess, wasn't even necessarily that the difficulty started over, I guess. It was just that the doors had been opened, and like now we were able to see just this vast landscape before us, and we understood. Yes, it's a fresh look. It was that we understood, finally, that, like, you can go to all this. You remember all those things we did in pre-calc? All those functions we looked at? All the trigonometry that you did? Yeah, now apply calculus to it. Go. Have fun. But, yeah, we, Yes, thank you, I teach it. and I'm doing... Oh, we're doing a thing now. Pre-calc, we've been doing this thing where we've been planning to have... Yeah. We've been doing this thing where we've had 2 classes, which are 3 credits each, that represent our pre-calculus sections. Functions and analysis. So... Okay. Two equal circles, so we got to make approximately equal circles. Totally good enough. Maybe I'm just reading it wrong. Bye. Okay, so ABC is a right triangle. Triangle ABC has 2 equal circles touching the hypotenuse. And one circle touches a side, and the circle is tangent to the other circle. So they're both touching the hypotenuse? Yeah. So it's a right triangle. sorry, did I exceed the maximum length? That's ridiculous. Okay. Circle. Touche. Alright, so like that. It's quite possibly horrible and doesn't look anything like what it is. Clearly, I'm having a hard enough time with that. Woo! So find all 3 side lengths in terms of the radius of the circle. Circles. No. Control Z. There. Okay, so we know these are tangents. We've just made a kite. Nice. Parts of it are going to be a little gross, but yeah. Overall, I don't think it's terrible. Alright, so then that's going to be the same. That are going to be the same. Depends on your definition of complex. Oh, you mean Heron's semi-perimeter formula? If that's it, I'm just gonna laugh. Okay, so I've done this before. We were trying to calculate the distance that a satellite is away from Earth. Coolio. How's it going? Yeah, because these are right triangles also. And if you... So if you make right triangles out of this, what we've got here is a way to relate the angle that exists down here with the angle that exists up here. I mean, those are complements, so it's not that hard. But based on your R, that now means that all of these have a representation that you can use. This angle, or this side length, is now going to be R plus this little bit here. So this is the altitude of the satellite, whatever you want to call it. So I'm guessing that you can probably also do the same with the third corner. It's awesome how terrible this is. Come on, do the thing. No, all right. That one was evidently such a bad line it would never make it. Alright, this is R. It's 2R here. The formula is so rare no one ever uses it. Hopefully you're not talking about law signs. Okay. So then this amount here is going to be R. This amount here is going to be R. This is probably overthinking it. But I do like the ones where we create the kites, because these are, again, like nice and symmetric, and it doesn't have to. All right. Can we prove anything about this stuff? I don't think we can necessarily say that this distance here is going to be the same as that distance there. It's like the R's are the same, but I think the extras here are different. So the sum of all of the angles on the inside of a circle is going to be 360. Right? So then... Yeah, sure. Can just, or at the very least, you can give me a big hint as to what it concerns. Hmm. Because we need the hypotenuse. All right. All right, so I know that that is going to be equal to that. So that. This one here is going to be equal to its own thing, not the other one over there. Hmm. This probably is not going to help, but oh, come on. Yeah, yeah. I was just seeing if that was going to randomly do anything, but nah. It's just more distracting. And we want those to be cosines because that would be dealing with r over, that would be our shared side here. Whatever we want to call it. r over that distance here, which is going to be r plus some distance x. Let this be x. Which is also equal to square root 1 plus cosine of theta, the entire theta, all over 2. And cosine of alpha over 2 be r over r plus y. Alright, if these lie on the hypotenuse, then it means that this makes a rectangle. C2 is going to be 2r. Alright, so I don't think I'm following you exactly on that one. What are simplex tangents? Or are you just talking to me? Going too far afield again. Not having any real flashes of insight here, sorry. Oy. Well, I could take a look at this later on. For right now, yeah, my half hour's up. Unfortunately. Okay, so all right, I'll take a look at this later, see what's going to happen. Can't guarantee much movement on it, but I've got a lot of other actual work, unfortunately, that I have to do. Well, thank you everybody for showing up. This has been fun. We're gonna get back in tomorrow and do some, I don't know, which one are we doing? Yep. Well, we were doing Valheim. So, I think I am still interested in doing Valheim. So we'll probably do some run up to the second boss to try to get the, what's the second boss? Back there. Yeah, that's the plant one. So probably I'm gonna start trying to figure out if there's another forest on my island and see what's going on there. Megalomorph, just in time for us to leave. Sorry. Amogus was having us try to figure out if we could find the perimeter of the whole thing in terms of R, the radius of either of the circles, which are the same size, and both lined up on the hypotenuse with one touching the edge of the triangle, or each one touching each edge of the triangle. So I recognize that we did a problem that was based on sending up satellites from orbit, or sending up satellites into orbit, and trying to figure out like how much of the Earth they were covering. So we've got this relationship uncovered where we've got half of alpha here, half of theta here, and Amogus gave us a hint there to use the half angle formula, but I'm going off on like algebraic tangents. So, but anyway, so tomorrow, probably more Valheim to try and do the run up to the second boss. And our seed is pretty nice. We've got this area that's just like flat plain for pretty much 200 yards in every direction. So if anything comes, I'm gonna see it. Yeah. So go see if I can explore some more, and then see if we can find more forest area, which is really what I need to do. So we are gonna head over and let's go see Selena, who is playing Super Mario 64. So we'll raid over. Alright, so like I said, thanks for coming. I'll see you all on either Friday, tomorrow, right? Because today's Thursday. It's now Friday. Alright, I'll see you in like 21 hours. So, have a good one, everybody. See you later. This is Obi-Wan Pez for N Simplex Pachinko. I'm going to raid out here in about 5 seconds.